Hello, everybody. In today's lesson, I will demonstrate you the assignment of molecular vibration to the corresponding type of symmetry operation. So as an example, I will be using the quite exotic example, which is called diazirinone molecule. So it made from our three-member twin, carbon, nitrogen, nitrogen. Nitrogen has double bond, and external carbon-oxygen bond. This molecule, when it decomposed to two stable molecules, nitrogen and carbonyl monoxide, can release about 100 kilocalories per mole, so it's high energetic molecule. So this molecule belongs to C2V group symmetry, and we put the as XSZ along the CO bond, and axis X will be also in plane of the molecule, and Y axis will be perpendicular to the plane. So this is so-called character table for C2V symmetry. It has four symmetry elements. E, it's so-called identity element, which does not do anything symmetry operation except just remain in the property of the molecule by itself. C2 is a twofold axis, which is in our case is coinciding with axis Z. And there's two symmetry plane. One is XZ plane is corresponding corresponding to the molecular plane, and YZ plane is perpendicular to the molecular plane. So the reason I selected this molecule is quite personal. Almost 30 years ago in '94, I did calculation of this molecule and published the paper jointly with Professor Schleier and Professor Boyd in the journal. It's called Chemical Physics Letter. So about 30 years ago, just studying one molecule of small molecule could be a scientific research. So about 17 years later, this molecule has been identified by infrared spectra, and has been found experimentally. So that's the reason I selected this molecule. So it's kind of personal, as I say. So let's now go to share the screen again and open IQmol. And let us build this diazirinone molecule. So I can do it in the following. So I select carbon initially, build this frame using just carbon atoms, create a double bond here, double bond there, and then replace carbon by oxygen here, and carbon by nitrogen here in a cycle. So now let's do it preliminary optimization using molecular mechanics. So so now we can see if this already has C2V symmetry. For this reason, we click on build and show the symmetrized molecules. So, and it showed that the molecule, so in the left bottom corner, that the molecule has C2V symmetry. Now, in order to get the frequency, we need to optimize the molecule and then calculate the frequency. For this reason, we go to Q-Chem setup. The job now one will be geometry optimization, and the job number 2 will be frequency calculation. So all I need to do is just click on the submit job and start Q-Chem on our server in California. As I mentioned earlier, it's free within 10 minutes, and I can do it and then get the result on my computer. So in this case, I don't need to repeat this calculation, but I already have done it. So all I do, instead, I go and open a directory where I already have the results. So saved it on my desktop with a name and 2CO. So I select the folder, and I get the result here. So, all right, so now let us just slightly increase so we can better see. And now let's just analyze their vibration and assign them to corresponding symmetry operation. So we click on frequency, and we see there is a 6 frequencies corresponding, 6 vibration frequency corresponding to this molecule. So it's easy to see why it's 6. So we have 4 atoms. So the total number of freedom for each, 3 are degree of freedom for each atom. So we'll get 12. Then we subtract 6 out of this, which correspond to the 6 degree of freedom for this molecule as a total. Okay, so and now we'll have 6 of them. So let's start from the lowest one. Okay, so as we can see, the vectors show that this vibration is along the axis Z, and obviously it will belong to A1's type symmetry. Oh, by the way, you can, if you go back and print this from the screen, the table of symmetry, of character symbol for C2V. So you will see what I'm doing because I'm just simply looking on the table, which is nearby. Okay, so the first vibration is A1. So we can also, if we double click, we'll see the vibration. So it mostly corresponds to vibration of CO double bond. So next one is, as we can see, it's also fully symmetric. So all symmetry operation, rotation, it's in plane. And also if we rotate it along the axis, it will be symmetric. And also if we reflect it in the plane perpendicular to the molecule, it's also symmetric. So this vibration is also A1 symmetry. And if we double click on it, so we'll see that most of it vibration of nitrogen bond, a little bit of carbon oxygen bond as well. Okay, so let's go to the next one. So this vibration has a vector corresponding to axis X, and so since it's in plane, so it's in plane, so it obviously will be either A1, but it's not A1. So, but since it's in plane, so it belongs to B1. So it's symmetrical with regard to reflection for in plane, but anti-symmetrical with regard to rotation and along the two-folded axis, and also anti-symmetric with regard to the plane perpendicular to the molecule. And we can see what it is. It's just shaking like this, almost like a dance. Okay, so the next vibration. So this one to me looks also very symmetric. So and so it's obviously it's also in plane. So this is also A1 symmetry. Symmetry to belong to A1 symmetry operation. So and this is for most of it, it's vibration of is stretching of nitrogen carbon bond. So next one. So this is actually is perpendicular plane vibration. So if it's perpendicular to plane, it might be either so it would be anti-symmetric with regard to our rotation along the C2 axis. So it's either B1 or B2. So to be B1, it has to be negative with regard to YZ. axis. So which is, let's just yeah, so it's negative with regard to reflection in the plane, in the molecular plane. So that would be then B1. So this would be B1 again. So let's just double check it. So it's negative with regard to reflection of C2. It's +1 with regard to reflections in actually I'm sorry, it's actually B2. So oh yeah, I did the mistake. So it's negative with regard to rotation along the axis C2, and it's also negative with regard to reflection in the molecular plane. So it's positive with regard to with regard to the perpendicular plane. So it's actually B2, B2 type symmetry. So, and the last one is also in plane vibration, but we see it's definitely not symmetric. So if it's in plane, so it's either A1 or B1. So, but it's definitely not A1 because it's not fully symmetric. So, and it's will change the sign if it's reflected in axis C2 or perpendicular to molecular plane. So this would be the this would be B1 vibration. So let's double click on it. So yeah, that's how it's look like. Okay, so also kind of like a dancing. So it's for most of it, changing the angle between the cycle and CO bond by nature. Okay, so they will did the assignment of symmetry assignment of this vibration. So just for collection, so let us go and also assign a couple of orbitals, which would be highest occupied molecular orbital and lowest unoccupied molecular orbital. So let's just calculate it. So this will show you the highest occupied molecular orbital. So if it's in plane, so this would be either A1 or B1, but it definitely B1 because it's not symmetric. It's anti-symmetric with regard to reflection of the perpendicular plane and to the C2 axis. So it would be B1. B1 type of symmetry for this highest occupied molecular orbital. And if it's C, it's a non-bonding orbital. It's mostly located on carbon and also partially on nitrogens as well. Okay, so now take a look at the lowest unoccupied orbital. So it's p-type orbital. So that means it's change the sign with regard to reflection in plane. So it would be either A2 or B2. So since it is since it's change, so when if it rotated along the C2 axis, so the sign would remain. So that's it, which means that it is B2 type of orbital. So that's how we do analysis of no, again, yeah, just a second, I think. Yeah, it's no, it's not changing their sign with regard to C2. Okay, so I did the mistake. So it's actually so it's actually would be yeah, it's A2. It's A2 type orbital. So because it doesn't change sign with regard to rotation around C2 axis, but it changed the sign in reflections of the plane perpendicular to the molecular plane. So it's actually A2 type orbital. So you see, it's maybe a little bit tricky when you just have to carefully see slowly what type orbital it has. By its nature, it's non-bonding orbital, which is p-type p-type orbital on nitrogen. So non-bonding orbital, two non-bonding are two electrons of non-bonding characters on nitrogen, and it has p-type symmetry. So that's example I wanted to show you today as a lesson to show how we would assign the molecular symmetry to the vibration. Thank you very much for your attention.